So our next speaker
Hi,
is
everyone.
Aleksander Lasek. He's from University of Maryland, and he's working in QICS. He did his PhD from Cambridge, and he has moved to University of Maryland to work on quantum thermodynamics. And he will be talking about experimental observation of thermalization with non-commuting charges. So
Thanks for the introduction. Hi, everyone. As Aisha said, I'm from University of Maryland, and today I'd like to present our work on experimental observation of thermalization with non-commuting charges, which we did in collaboration with Christian Roos and Rainer Blatt's experimental group at University of Innsbruck, who of course did our experimental part. And our preprint is available on arXiv under the link visible on the screen if anyone's interested in looking it up. The aim of this work was to investigate the thermalization of quantum many-body system using a quantum simulator. And the quantum simulator here means an experiment that can engineer a certain Hamiltonian in a many-body quantum system and measure its behavior. And we want to investigate the predictions of the quantum thermodynamics. And in our context, quantum means non-commuting. So we focus on the non-commutation of operators as our good definition of what quantum means. We also want to answer the question whether the effects of non-commutation of charges are actually detectable in an experiment that we can do. Our work, I think, is relevant because it's bridging two fields, the field of quantum simulators with the emerging field of non-commuting quantum information theoretic thermodynamics. And both of these fields are very interesting in their own respects. Here we combine the two of them in a first of a kind experiment. And our main claim to fame here is the first experimental observation of this novel quantum state that's predicted by quantum thermodynamics. Let's start with a background on thermodynamics, not just quantum, but in general. I'll present a basic theory basis behind our experiment. So a common setup in thermodynamics is such that you have some small system of interest S that will interact with a larger environment. So here we represent both the system and the environment as comprising of some spins. So we have a chain of spins, which is actually also the setup in our actual experiment. And we'll have two of these spins to be a small system of interest. And they will interact via some Hamiltonian with the rest of the spins, which will form an effective environment. So the system S is able to exchange some quantities, which we call charges, Q, with the environment. And charge in thermodynamics is just some conserved quantity. So it could be, for example, particle number energy. It doesn't have to be electric charge, actually. Or it could, for example, be a spin. And under this setup, the system S is expected to thermalize to some thermal state, rho thermal. So after the dynamics is settled, we expect the system S to reach the equilibrium with the environment, and it will be in some average state, thermal state, rho thermal, that predicts its long-term quantities of the system. However, what happens if the charges do not commute? So I gave an example of energy and particle number. So if they're charges, that means they're conserved. If they're conserved, then they will commute, right? If the number of particles is conserved, then it will commute with the Hamiltonian. But what happens if the charges do not commute? For example, spin components. So can the system even thermalize in this case? So let's pick, as I said, our three charges to be the three spin components, Sx, Sy, and Sz. And of course, we know that any pair of them enjoy a non-commutation relation such that their commutator is proportional to the other third charge. So the 3 of the charges just don't commute in any combination. We can read more about non-commutation of conserved charges in this paper in Phys E by Nicole Junger-Halpern. Well, when the charges don't commute, they cannot have well-defined values simultaneously because they don't share an eigenbasis. So if they cannot all be in eigenstates of some particular value, then in what state do we initialize the system? Usually we would initialize the system in a microcanonical subspace, which is a subspace which has well-defined values of the conserved charges, but here with non-commuting charges, that's impossible. So we have to generalize it to a so-called approximate microcanonical subspace. So a subspace that, let's say, has fairly well-defined values of the charges at least. And we'll say that we'll demand that each of the charge has variance that is at most n to nu in the system size. So we want the variance to grow slower than the size of the system. And that means that as the size of the system grows, the expectation value of the charges will grow proportionally to it, but the variance will grow less than proportionally to the system size. And that's our condition that we pick to be able to say that the values of the charges are approximately well-defined, fairly well-defined. And we can read more about the theory between these resource theoretic statements in quantum thermodynamics in this paper in Nature Comms by Nicole. So for our non-commuting charges, we're going to propose a non-Abelian thermal state as the proposed state that the system is supposed to settle to. And non-Abelian here is because the algebra of the charges is non-Abelian because they do not commute. And this thermal state has a fairly familiar form. So we still have an inverse temperature beta, which is 1 over kBT. And the exponent, we have the Hamiltonian of the system of interest. And the superscript 2 here, it's not a square. It means that the operator refers to the 2-qubit system of interest. So we have a chain of ions, of many ions, and we pick 2 of them to be the system of interest that interacts with the rest, which is the environment. And when we talk about the thermal state of the system, it will be the thermal state of the 2-qubit system of interest. Therefore, the operators have superscript 2. So this is a generalization of a Gibbs ensemble, and it's generalized by adding this extra term with chemical potentials mu and the charge operators q. And we add however many charges we have in the system. In our case, it will be 3, the 3 spin components. And the common thermodynamic arguments to derive this form of a state assume that the operators commute, and here they do not. So we want to ask, how close does the system actually get to this state? Additionally, I've written down the form of the state for a 2-qubit small system of interest, but because our interactions are quite strong, to get an accurate thermal state, we might actually have to go beyond 2 qubits. So already we can improve the accuracy of this thermal state by going to a 4-qubit system and tracing out the outermost 2 qubits, or even, if possible, to write down the thermal state of the whole system and then trace out all but 2 qubits to calculate our thermal state. Additionally, what does temperature T here mean here? It's not actually proportional to the average energy in the system because of the extra terms that are related to the charges and the exponents. So the interpretation of T is a little bit more general. It's not just proportional to it's not just a measure of the average energy, but also takes into account the expectation values of the charges. And we can read more about thermodynamics of systems with multiple conserved quantities in this paper in Nature Comms by Gurianova. So in our experiment, we want to pick a good initial state to start with. And by good, I mean a state that will make the observation of the non-Abelian thermal state, or the NATS, easy and possible. So our initial state, psi 0, is what defines the parameters beta and the mu's. So that's what defines the temperature and chemical potentials. So let's write down the thermal state of the whole system plus environment. And in this case, the expectation value of the Hamiltonian is what defines beta, and the expectation value of the charge operators is what defines the chemical potentials of the charges mu. So what kind of initial state is good for observing the NATS? What qualities do we want it to have? We want it to be, as we said before, in this approximate microcanonical subspace, so that it's meaningful thermodynamically. And that just means that the variances of the charges, we don't want them to be too large so that everything is random. We want the charge values to be fairly well defined. We want the charge expectation values to be high to make non-commutation more visible, because if the charge expectation values were low or close to 0, then our non-Abelian thermal state would just be reducing to a Gibbs ensemble, so we wouldn't be able to see any difference. We also don't want to have too high of a temperature, because states with high temperature will be very close to the maximally mixed state. And if everything is close to the maximally mixed state, and we also decohere towards the maximally mixed state in the experiment, it will be difficult to observe or measure or distinguish anything. So we want to have the temperature as low as possible, given all the other constraints. We also want the state to be simple, or at least possible to initialize experimentally. If the initial state was highly entangled and complicated, it would take a lot of time in the experiment to initialize it, and that will be time during which errors could act and time generally lost that is not available for running of the actual experiment. So we want the state to be easy to initialize. So we're going to try a product state. So we've come up with a state that is a product of 3 single qubit states, which are eigenstates of spin. So let's say it's an eigenstate of y positive spin, x positive, and z positive, and then repeat it however many times we need to build up our full system. And within the block of 3, the order here is arbitrary. So we could equally have x plus, y plus, z plus, etc. Or we could have y minus, x minus, z minus. But the placing of these eigenstates in the whole total chain is not arbitrary. So we don't want, for example, 2x eigenstates to be next to each other, as that will increase the temperature. So this is a state that has high charge expectation values and also reasonably low temperature, which will, as we discussed, make it as easy as possible to observe the non-Abelian thermal state and distinguish it from other thermal states in an experiment. And here's a picture schematic of our experimental setup. We have a chain of ions that are trapped in a magnetic field in a linear polytrap. And these ions are essentially qubits, 2-level systems that can be addressed individually, and that they can have an engineered Hamiltonian acting on them. And then they can be measured at the end of the experiment. So let's go into a bit more detail about the experiment. So it's a trapped ion quantum simulator. We have our chain of ions inside the trap, and calling back to the previous diagram, that's going to be our system of interest plus the environment. So we're going to pick some 2 of the ions to be our system of interest, and the rest will act as the effective environment. And the system and the environment can exchange energy in the free spin components. However, under the Hamiltonian that we're going to pick, the free spin components will be globally conserved, so they will be our charges. And we're able under this setup to have between 6 and 15 total ions for this experiment. And the ions are, it's a string of calcium 40 ions that's confined in the trap. And each ion encodes a qubit in the Zeeman states with different quantum numbers. And effectively, it is a chain of 2-level systems that are individually addressable. So they will correspond to the Z plus and Z minus states in the Z basis of spin. So in our experiment, I mentioned that we're going to have to pick a Hamiltonian to implement. And in this experiment, we want the Heisenberg Hamiltonian because it conserves all the spin charges. So we wanted our spins to be conserved so that they can be charges, because charges are conserved quantities. And the Heisenberg Hamiltonian, which has an XX plus YY plus ZZ coupling, is what achieves this. However, the native coupling in the experiment is just an X-type Ising Hamiltonian. So natively, the ions are only coupled by an XX coupling and within 1/R to the alpha type interaction. Alpha is actually very close to 0, so it's almost 1/R interaction. So how can we take this interaction and turn it into the Heisenberg Hamiltonian? We can use a Trotter scheme. So we're going to let the system evolve under the XX coupling for a little while. Then we're going to rotate the X-axis onto the Y-axis so that we're effectively doing an YY interaction. Then we're going to rotate onto the Z-axis so that we're implementing a ZZ interaction. And on average, we will be implementing a full Heisenberg Hamiltonian. And here's a schematic of the gate scheme we use to implement the Trotter scheme described. So at the basic level, we're just going to do a ZZ, YY, and XX interaction by rotating onto different axes in between. We additionally implement a dynamical decoupling scheme to reduce our errors by inserting additional Rx and Ry rotations. And finally, we split this into 2 blocks that basically implement interaction on the positive axis and on the negative axis so that we reduce additionally rotation errors for an experiment that is generally quite resistant to decoherence. And in general, we could engineer different types of interactions, which we'll come back to later. However, for the main experiment, we want the Heisenberg Hamiltonian. So we've discussed the initial state and the experimental setup, and then what do we actually do in the experiment? How do we quantify the thermalization? We're going to evolve our initial state under the Heisenberg Hamiltonian. Then we're going to use quantum tomography to estimate the 2-qubit density matrix for all small system choices. So let's say if we have 12 qubits, we have 11 ways of choosing adjacent pairs, and we can average over all of them for good statistics. And then we're going to calculate the average relative entropy to the non-Abelian thermal state. So we've chosen average relative entropy, or just relative entropy in general, because firstly, via the binary testing hypothesis, it's related to the probability of discriminating between 2 states, which is essentially what we're doing. We want to see whether the observed state is more like the NATS or more like another thermal state. And secondly, Nick Hollinger-Halpern has previously proved some bounds about the relative entropy in the quantum thermodynamics setting. So we want to stick to a measure that we already understand and have something proven about. So as I've mentioned about the other thermal states, we need some other comparison to actually show that the non-Abelian thermal state is the best prediction. So we're going to also calculate the relative entropy distance to other two commonly used thermal predictions. We're going to use a grand canonical state, which instead of 3 charge operators only has 1, the Z spin. And we call it the grand canonical state because the SZ operator is equivalent to a particle number operator by a Jordan-Wigner transformation that would usually be there. Additionally, we're going to compare to the canonical state, which is just a thermal state that pretends only energy is conserved. So there's no other spin charges conserved, just the energy. And here's the main result of our experiment. It's a plot of relative entropy of the experiment to the 3 described thermal states versus time. So our experiment runs for 15 milliseconds, which is time that is sufficient for good thermalization. Ideally, we would want to be able to run the experiment as long as possible, but there's a trade-off between better thermalization and increased error rate. So we've determined that 15 milliseconds is an optimal time that enables us to reach really good thermalization, if not complete, but at the same time, the errors will not be too large to throw off our results. And here we can see the experimentally measured points as the points, as well as the simulated exact result as the solid line. Excuse me, as the simulated trotterized result is the solid line, and the dashed line is the simulated exact result. And we can see, firstly, very good agreement between the exact and trotterized result, which means our trotter scheme is correct and appropriate for the experiment. Secondly, we can see that we have really good agreement between the theoretical simulated result and the measured result for the grand canonical and canonical systems, which are the yellow and the green points respectively. Although we can see that because of the coherence, the measured points gradually get lower and lower below their theoretically expected lines. However, we can see for the non-Abelian thermal state, which is in blue, that the measure points actually stay just right on the expected theoretical line. So it seems like the non-Abelian thermal state is somewhat more resistant to noise, and we'll come back to that fact in just a minute. However, the most important takeaway from this plot is that the NATS has the lowest relative entropy at each point in time, and most critically has the lowest relative entropy at the final time when the dynamics have settled and the system is thermalized. And that means that the non-Abelian thermal state is the best prediction of the actual experimentally measured state. So it's better than the grand canonical and the canonical states when we have 3 non-commuting conserved charges, which means that we can effectively say we have observed the non-Abelian thermal state. It's the best prediction out of the 3, and it's really close. Additionally, we've measured relative entropy for different system, total system sizes. So that's the relative entropy at the final time when the system is most thermalized. And we've taken measurements for 6, 9, 12, and 15 total qubits. And again, for each size, the non-Abelian thermal state is the best prediction with the lowest relative entropy. And as well, we observed that as we increase the total number of qubits, the relative entropies for each prediction decrease as well, which is expected. However, unfortunately, with only 4 data points here, we're not able to answer whether these predictions would converge in the limit of large N, and would they all go to 0 in the limit of large N as well. So we're actually thinking of extending the experiment a little bit and adding some points for larger system sizes, which will perhaps enable us to answer that. we're additionally constrained to multiples of 3 qubits because of how our initial state is defined. An additional question is how much the thermalization is actually inhibited by the presence of non-commuting charges. So let's run a second experiment where the Hamiltonian will only conserve one spin charge. So let's call it an XY Hamiltonian that only has an X coupling and a Y coupling. And this Hamiltonian only conserves the Z spin charge, for which the grand canonical thermal state should be the best prediction. So only the total Z spin commutes with the Hamiltonian. And we're going to see if indeed now the grand canonical thermal state is the best prediction, and compare it to the previous case with the non-commuting free charges for which the NATS was the best prediction. So here, again, we measure the best thermalization versus the total number of qubits. And we see that indeed the grand canonical thermal state has the lowest relative entropy. And then additionally, what's important, that entropy that grand canonical thermal state reaches for each qubit is lower than in the previous slide, the relative entropy that the NATS was reaching. So not only for the XY Hamiltonian is the grand canonical thermal state a better prediction, it also gets closer to the exact state than the NATS was getting in its respective case. So this tells us that the presence of the additional non-commuting charges actually disrupted thermalization. The system has thermalized less to the NATS than for free non-commuting charges, then the system has thermalized to the grand canonical state with one conserved spin charge. Additionally, let's come back to the point that I made that the NATS seems to be more resistant to noise. So here is a plot of simulated exact evolution as well as evolution with simulated noise for the non-Abelian thermal state, the grand canonical state, and the canonical state. This simulation is for 9 qubits, but it's very comparable to the 12 qubit results that we saw for the main experimental plot. So firstly, let's talk about the straight, solid, and dashed and dotted lines. So these are the relative entropy of the NATS for the solid line, grand canonical for the dashed line, and canonical for the dotted line to the maximum mixed state. So the thinking is that the polarizing noise, which approximates our experimental noise well, is bringing the state towards the maximum mixed state. So as the noise takes effect, our relative entropies in each case should be tending to these limits. So we would expect that as the state gets closer and closer to the maximum mixed state, the relative entropy of the grand canonical to the depolarized state will, for example, tend to this dashed line, because that's the relative entropy to the maximum mixed state, right? And we can see that it indeed happens for the canonical and grand canonical predictions. For example, the grand canonical exact prediction is the green squares, whereas the grand canonical depolarized result with added depolarized noise is the red triangles. So we can see that the red triangles drop below the green points as time goes on. So the dynamics are settling and the green points are reaching the limit of thermalization. However, with the noise, we're dropping below that limit and towards the dashed line, because that's the relative entropy of the grand canonical to the maximum mixed state, and we're going towards maximum mixed state as we're adding more and more noise. Similarly, the relative entropy of the canonical state to the to the depolarized result is dropping, and it will drop towards the dotted line. However, we can see that for the blue and blue circles and orange triangles, which is the exact NATS and depolarized NATS result, they are staying very close within the experimental runtime of 15 milliseconds. So we'd expect generally that the depolarized result would tend towards the solid line, so it would increase. But that does not happen as fast as it does for the other predictions. So it looks like the non-Abelian thermal state is actually fairly resistant to noise, which is also very good for observing it, because if that wasn't the case, the relative entropy of the NATS with noise would actually be increasing, because the limit for the NATS is the solid line, which is above the exact NATS result. So we would have a case where the relative entropy of the NATS is increasing, whereas the grand canonical and canonical ones are decreasing. So they would cross over, and they would make it difficult for us to distinguish which state is better, which state has lower relative entropy. However, thankfully, that doesn't happen, and NATS is resistant to noise. So despite the other two predictions dropping in relative entropy, our noise is low enough that the NATS still remains the best prediction significantly, and it has the lowest relative entropy at all points in time. Additionally, here's a plot of that explains pair-to-pair fluctuations. So for all 11 pairs in our 12-qubit total system, as a function of time, we have the relative entropy plotted here. And we can see that initially the relative entropy is very high for all qubit pairs as expected, because they're not thermalized. And then as they gradually thermalize, we can see the finite system size effects and fluctuations, as different pairs generally have slightly different relative entropies. And as we could guess, the central pairs thermalize better than the edge pairs because they have more neighbors to interact with. However, the system is still fairly uniform at this system size, so edge effects and finite system size effects are not overly strong, and they're not overwhelming our actual result. So to conclude, here we report the first experimental observation of this non-Abelian thermal state, the NATS. We show that realistic systems can exhibit signatures of non-commuting charges, and we can actually observe them in an experiment despite decoherence being present. Because firstly, we can control the decoherence and minimize it with our Trotter scheme and dynamical decoupling. And secondly, the NATS is more resistant to noise than the other thermal predictions. And then we also show that our small system of interest thermalizes less in the presence of non-commutation. So when we have 3 non-commuting charges, our system will thermalize less than if we had only 1 spin charge, which was the comparison between the Heisenberg Hamiltonian and the XY Hamiltonian. We also developed this quantum simulator toolkit that we demonstrate that we were able to engineer both the Heisenberg Hamiltonian and the XY Hamiltonian in our trapped ion chain. And generally, there is much more flexibility and capability here to implement other types of Hamiltonians for other types of experiments. So this experimental setup is not completely specific to what we wanted to do. They would be able to implement other Hamiltonians with other system sizes and other interactions, different initial states if needed, etc. So we want to show that the toolkit is fairly general. It's not completely specific to this experiment. We're also here opening the door to experimental testing of this novel and rapidly developing subfield. So the field of non-commuting charges was theoretical until now, and we started the experimental testing of it and show first experimental results and observations. I'll talk briefly about some future work and future avenues. So I've mentioned that we're not current with the current data, we're not fully able to distinguish whether the gaps between the free thermal predictions relative entropy close and whether they go completely to zero in the limit of large n. We're hoping to take more data for larger system sizes and try to extrapolate the behavior to be able to answer it with a better accuracy. But in some sense, our current result is still meaningful because real systems that we can explore are not thermodynamically large, and we already demonstrate that if we have tens of qubits, the effects of non-commutation are present and significant. Additionally, we want to answer how much the observed effect is caused by having more charges rather than them being non-commuting specifically. So we compared 3 non-commuting charges to 1 charge. And the question is the difference because we had 2 more charges in non-commuting case? Or is it because we had the non-commutation between the 3 charges? And we're currently working on a project that attempts to answer that. And thank you for your attention. Again, our paper is available online. Experimental observation of thermalization with non-commuting charges on arXiv. We've actually made a small alteration to the data from the preprint. We've had to fix one error. However, none of the conclusions have changed. So I've presented the updated data here, but the paper on arXiv, the preprint, is still good to read, and I recommend checking it out. Thank you, and I'll be happy to take any questions.
Thank you very much, Aleksander, for a very nice talk, enlightening, in fact. Any questions? You can post your questions in the chat. Meanwhile, while doing these experiments, you reach a steady state, right? When the system is stable. But there is a region in which the relative entropy is very high. Is that region in the initial time? Is that region of some quantum information processes?
So I think we wanted to go to a time where the system is well thermalized, because that's what we can describe with thermodynamics. It does turn out that the NAT has lower relative entropy at all times, but at these lower times, that we don't think the results are necessarily that meaningful. But as you say, relative entropies are large because the system is very far from equilibrium. It's just the initial time.
Mm-hmm. Okay. So there's a question from Akash Kundu that does non-commutation of any conserved quantities termed as NATs or just charges?
So the definition of charge is separate from what is non-commuting. So the NATS is the non-Abelian thermal state. So it's the thermal state that we predict the system will thermalize to if we have non-commuting charges. But you can also just have charges that are either commuting or non-commuting, and that's just the definition of a charge. It's a conserved quantity. So the non-Abelian thermal state is the thermal state that a system with non-commuting charges will thermalize to, but you can have a definition of a charge that is separate from that word, if that was a question.
Thank you very much. Any further questions? So we thank Aleksander again, and if anybody has further questions, there is a Discord channel for Aleksander, and you can put your questions there. He may visit that and answer your questions. And thank you very much, Aleksander, for being here. It was very nice to have an experimental talk, in fact, and a very cutting edge research. So many thanks. So I stopped the recording.
Mm-hmm.